Great to see you here. I hope you're having a good conference. My name is Bruce Momjian. I am one of the Postgres core team members and member of Enterprise DB. I've worked there for 9 years. And what I'm going to be talking about today is the selection of hardware for databases. I've found this to be a very overlooked topic. I'm going to explain why. And I think that there's a lot of value that can be had by studying optimal hardware for databases. If you wish to look at the slide deck on your laptop or some future time, right here is the URL for my presentation. So it's basically my website. There are probably 30 presentations on that website, so if you'd like to look at some of the other ones, feel free. There's also a lot of videos of me giving this presentation and others. So feel free to look at that. I will be taking questions as I speak or taking breaks. So again, I'll stop. I'll say, are there any questions? And give you a chance to sort of interact. Me talking is sort of interesting, but you talking is even more interesting, particularly to me. So I think it's nice to sort of get feedback and get an idea of what kind of questions you have. So again, we have 50 minutes. We have 26 slides, so I think we're going to be good. I have a little demo I'm going to do to kind of give you an idea of some of the stuff I'm talking about. So I hope you'll find it enjoyable. So what are we going to talk about today? You might think, when you think of databases, that this is going to be what we're going to focus on. You hear these terms a lot. We get a lot of people who post to the email list and say, oh, I'm thinking of a new server, and it has this many CPUs, and it's this architecture, and Sandy Bridge, or whatever it's called. I'm making up names. But a lot of these people are just used to speccing out game machines. Or application servers, or servers that really aren't databases, because frankly, these are not the important terms for a database. Yeah, you need them, and yeah, they can be important at some point, but they're not necessarily the place I would be looking from day one, okay? Just to reiterate my point, when you think of your server, your database server, you're probably thinking of it this way. You're probably thinking of your CPUs as the first thing, because that's where all your code is running, that's where the database server runs. That's kind of the area I want to monitor first, right? That's probably what you're thinking. And then your memory kind of comes in second, and maybe when somebody's speccing out the server, they're going to tell us how much memory they're going to use. They're not usually going to tell us how many DIMMs there are, or what type of interleaving they have, or so forth. That often doesn't actually come up. And I/O, embarrassingly, actually becomes this sort of tiny little thing at the bottom. They'll say, oh, I have this much disk space, right? But is that really the last thing you should be telling me? I would argue that for a database server, you should think of it this way. The I/O should often be the thing you think of first, okay? You put your money in there, you put your monitoring in there, you make sure that that's optimized first. Then the memory, when you're speccing out a server, okay? And then the CPUs. I cannot tell you how many times people have spec out a database server, and obviously they put, when you spec out a server, typically you're going to spend what, $4,000, $15,000, whatever, and of that amount, certain portion is allotted to the I/O, and certain portion to which CPUs you're using, and certain portion to memory, right? I mean, it just makes sense when you look at the parts list, and you're going to look, and a lot of times people will say, well, I can get this faster CPU, it's going to cost me an extra $1,200, or I can get this much additional memory, it's going to cost me the same amount of money, or I can get a different type of I/O system, and that's going to cost me X. And a lot of times those trade-offs are not really made in a way that's optimal for databases. And one of the goals of this presentation is to kind of sort of retool that, and also to give you ammunition, because a lot of times when I've presented this talk, people will come up to me after and say, you know, I've talked to this about the person who purchases our equipment, and I've never really been able to get it across, but he said, I think if I show them this slide deck, I think I might be able to get through to them. So again, what's one of the things I'm going to be going over here is the concept that the selection of hardware requires a different heuristic, a different analysis, a different weighting for a database server than it does a normal server, and I'm going to explain exactly why in a minute. Okay. Any questions so far? I know it's very general, but great. Okay, so let's go. So why the difference? Why do we have to look at a database server differently than we would a traditional server? The first thing is the real difference is workload, okay? Because when you think of the workload for a traditional server, I'm talking like an application server or a web server or a mail server or whatever, okay? You're looking at network overhead, HTTP traffic, things like this, parsing, text processing, which would be email, virtualization overhead for application servers, and application code, right? You got loops, you got function calls, all that stuff. That's what you're thinking when you're thinking of doing application server. And most application servers are really kind of CPU bound, right? They're not doing, you know, like if you look at these things, they're not doing a huge amount of I/O, right? Not really. I mean, I guess you could think of network as I/O, but it really isn't. It's network. It's through an Ethernet card. Text processing is through application code, all CPU bound, okay? But when you look at what a database does, it's really quite a bit different. And you can see the heavy I/O emphasis here. So sequential scans of large tables. What application does that? Not many. Not many non-database applications are scanning huge amounts of data. Usually if you have to use huge amounts of data, you're going to use a database. And by definition, that is going to be very I/O intensive. And that's why that pyramid that I showed you, I put that I/O is the big thing on the bottom. Index scans causing random I/O. Random I/O is almost, I want to almost say exclusively a database thing. I mean, you just don't see a lot of fseeks in code. That, yeah, okay, we do them occasionally, but not in a heavy performance type of way that a database does. Again, almost by definition, if you need to do a lot of indexing, a lot of random I/O, you're going to use a database because you want this fast access. Unpredictable query requirements, that's another one. Usually there's a fairly normal profile for an application. You know it spends X% in this portion of the code, and X% in that portion of the code, and it's predictable. You run it through some kind of profile, or you find out where the slow parts in your application, you speed them up, and you're done, right? Again, it takes a pretty well-defined input, and you get a pretty well-defined output. Database server is really a language interpreter, right? SQL is an expressive, it's a declarative language. It's not a language like C or Perl or Python where your imperative saying, hey, go do this and loop here and increment that variable. That's not SQL. SQL is a declarative language. You say what you want, you declare what you want, and you ask the server to give you the answer in the best way that it determines. So again, you have this very asymmetric load of demands on your server that is very atypical for pretty much any other workload. Reporting, that's another one. Huge amount of I/O requirement. Huge sort of, can take hours sometimes to churn through all the data. Again, very I/O intensive. What you really come across from here is that none of these really are CPU intensive, right? I mean, you look at that list, you're like, yeah, you're using the CPU, but it's not really what you're doing. The CPU is there to kind of enable a lot of I/O. So again, back to that triangle, that's why we end up focusing on that I/O part. Durability is an even bigger issue. And I'm going to be kind of harping on this as I get into some of the performance selections that you're going to have. This slide is actually from a different slide deck. it kind of gives you a really visual explanation of how the write-ahead log works in Postgres, how the shared buffer cache works, and how they interact with the kernel and the I/O subsystem. But the real part I want to focus on is, again, that durability part. Very few applications guarantee durability. What do I mean by that? Well, if you open a word processing document and you type a couple words and you hit save and then you pull the power plug right away. So you save your word processing document and you pull your power plug right away. If you restart that server, is that word processing document going to be there exactly the way you saved it? Maybe, maybe not, right? You don't really have an expectation when you save or close a typical application that if the next moment you lose power, that data is durably stored. And there's a bunch of reasons for that. But one of the contracts that an ACID database or any enterprise database has is that we actually guarantee durability. And what that effectively means is that if you pull the power plug right after you commit a transaction and then repower that machine, that committed transaction is fully recorded in the database. That's one of the reasons people use databases, because they don't have by default, Postgres is one of these, by default, you do not have the potential for data loss unless you've misconfigured your server. And I'll talk a little bit about what that means. But again, that's a further demand on that I/O subsystem. And I'm going to kind of go over the details of exactly how that works, what happens, and how you can improve that situation. Okay? So any questions about that so far? We're good. Okay. So let's take a look at a little bit of detail here, and I'm going to have to use my, my pointer here. So effectively, this flow of work, I should kind of go over with you because I need to explain that durability portion of what we're doing here. So what we have here at the top are 3 Postgres sessions, pretty standard, right? Over here in red, and it's a little small, I'm sorry to say, is that shared buffer cache, the area where you do all of your reading and writing. So anytime you're reading a block from the database, writing a block from the database, you're actually doing that in the shared buffer cache, okay? But when you write into that shared buffer cache, that data is not automatically pushed down to durable storage. So you can do a whole lot of things, do a lot of writes, a lot of updates, a lot of inserts, a lot of deletes, and effectively all you're doing is writing to this shared memory area. Now, if I tell you that shared memory area basically isn't written down right away and isn't forced to durable storage, what makes Postgres durable? And the answer really is on that right-hand side. For optimization reasons, Postgres has something called a write-ahead log. And the write-ahead log is basically a record of all of the changes that have been made to the database for every transaction that's currently running. It's basically an append-only log. You're adding rows, you're adding rows, you're adding rows to that write-ahead log, okay? You've probably heard of the write-ahead log for crash recovery. It's also used for streaming replication. It's used for point-in-time recovery. It's used for logical replication. Again, very important part of the system. But its original purpose was to give durability to Postgres. So how does that work? Well, you might notice that every time I have an arrow from one of the Postgres processes to the shared buffer cache, I have a second arrow that points to the write-ahead log. So effectively, every time you do a write or a change into that write-ahead log, into that shared buffer cache, you are also doing a write to the write-ahead log. Okay, so if you update 10 pages, we're going to have 10 records of row changes that are going to be written to that write-ahead log. And when your transaction commits, we're going to issue a special kernel call which forces that write-ahead log to the kernel, but also the special command actually says, not only do I want the data to go to the kernel, I want the data to actually be pushed down to the I/O subsystem. Okay? And that process of pushing the data down to the I/O subsystem is called an fsync. You might have heard that term before. There is an fsync parameter in the Postgres comp file, and that's effectively what it's telling you. It's saying, when it defaults to on, and it's saying every time I commit a transaction, I am going to force that write-ahead log to durable storage. And therefore, I am now fulfilling my durability contract. I may still have dirty buffers in the shared buffer cache all over the place, but that's okay, because I've written every change to this append-only log. And when I committed, I forced that log down to disk. So therefore, I know if I lose power after that commit, when I restart, I'm going to reread that write-ahead log from the durable storage. Then I'm going to replay it. I'm going to write them into the shared buffer cache, and I'm going to flush them down to disk. Okay? So that's effectively the way Postgres does durability. The reason that write-ahead log is there is because it's very expensive to write to fsync every single page or shared buffer that gets dirtied on a commit. It's much simpler to serialize all the changes in a common shared write-ahead log that gets flushed down to durable storage. Yes, sir?
So does Postgres support creating the file system raw, just a raw file system, so that I can avoid the kernel?
That's a great question. So the question is, does Postgres support the ability of creating a raw file system so I'm not having to have the overhead of going through the kernel? And the answer is we do not. We have talked about it for a long time. Obviously, it's a well-known technology. We have done some research on what it would take to remove that green area, okay, and effectively do direct I/O for every write. And what we found was that although eliminating that green area gave us a small benefit because we're not, obviously, we're not having that extra layer, okay, what we found was it made the system very brittle to workload changes. Because what happens, the way the system runs now is that you define your red area, your shared buffer cache, as a fixed size, okay? And that green area, the kernel buffer cache, effectively gets larger or smaller depending on what I/O demands are on the system. So if there's a lot of sorting going on, there's a lot of application allocation to memory, that area is going to shrink. If there's not as much, that area is going to grow. So effectively, what we found was that if we remove the green layer, that red area, the sizing that red area to match the workload became much more critical. So it's sort of like we could get an optimization from raw, but we felt that overall it would be a loss because, again, databases have a tendency to have a very variable workload, and that green area gives us sort of an elastic buffer that we can change sizes, okay? Because that area is used not only for the write-ahead log, but of course, when you run a checkpoint that I wasn't going to get into, we effectively write the pages down to the green area, the kernel, and then we wait like a couple minutes for the kernel to sort through not only our I/O requests, but all other I/O requests to that device, and then flush those down. And because the kernel kind of knows that storage layout probably better than we do, and it knows what the other outstanding requests are to that I/O, in a lot of ways it was easier to just push it down to the kernel and let it deal with that overhead. So it's a great question. We have looked at it. We just didn't feel that it was going to be enough of a win to really implement. Great question. Other questions? So as I was saying before, that fsync is going to happen. It would be very expensive if we fsynced every single dirty page, because then you're doing a lot of random I/O, and it's just terrible for performance. Effectively, fsyncing a single file that's just increasing is actually very, very efficient. And again, as I alluded to earlier, when a checkpoint happens over a couple minutes, and unfortunately I don't have a slide. I have a slide on my website, but not here, that talks about how a checkpoint works. It's actually it's basically a writes over several minutes that allows you to kind of slowly trickle the I/O down into the system so you don't get spiky workloads while that's happening. So again, another advantage of using the kernel is it kind of buffers it and allows us to spread out and aggregate other I/O requests kind of together. But again, that fsync part is really critical. Just to give you a real specific example, I'm going to take this slide, I'm going to blow up this section here, okay? So I'm going to take that slide, I'm just going to blow up that bottom section, I'm going to break it apart, and I'm going to open up the section between the kernel cache and the storage to give you an idea of what's there. So here's a little bigger picture. We still have the shared buffer cache, we still have the write-ahead log, we still have the fsync going on. We have the magnetic disk here at the bottom. I'm going to talk about SSD in a minute, but the magnetic disk here at the bottom, and now we have some layers between there. So we have the kernel, then we have what we're going to call an HBA, host bus adapter, which could be a RAID controller, and it may have a cache on it. So this would be your I/O controller, your disk controller, inside the cabinet of the server. Then you have a disk cache, which exists obviously not in the server, but in the disk itself. Almost all modern disks have a certain amount of memory that exists inside the disk enclosure. Okay, and then obviously in a magnetic case, you've got the magnetic platter spinning around. Okay, so what's interesting here is when you do an fsync, a properly configured system is going to, if it does not have a durable layer, that fsync has to be passed down to the layer beneath it, and then only once the layer beneath it has acknowledged the write can it then acknowledge the write up. So for example, if I fsync to the kernel, obviously the kernel has no durable storage, so it's got to pass its fsync, its durable request, to the host bus adapter. If the host bus adapter has a battery, for example, like here, okay, it can acknowledge the write directly. It does not need to pass it to lower levels because it has durable storage right there. And then at some later point, it can then write it down to the kernel, the disk cache, and obviously down to the magnetic, okay? But if you don't have a battery, then you have to effectively pass the fsync farther down. You've got to pass it to the disk cache, and then the disk cache, particularly on magnetic drives, there's no battery usually, almost never. So you have to then wait and get it down to the magnetic disk. So you've got all these layers that you've got to go through, and that magnetic disk is super slow, to the point where even for a 15,000 RPM drive, you're probably looking at only 250 fsyncs a second. So you might have, a 3.2 gigahertz CPU, but you're going to be throttled by default to guarantee durability on a magnetic disk system that has no durable cache. You're going to be throttled at 250 fsyncs a second, okay? And that, if that is your system now, then you're leaving money on the table, because obviously you've got your CPUs and your system running very quickly, but you're choking performance because we're being throttled by that storage layer, and the only durable place we have is the platter, and we got to wait for that platter to come around. So if you do the calculation, 15,000 RPM divided by 60, it's about 250, okay? And if you have anything slower than 15,000 RPM, it's going to be even less, right? So again, one way of addressing that is to add a battery in the HBA, and a lot of people do this. Yes, sir?
So is it not efficient to, when we enable the RAID cache, it's not efficient to disable the disk cache?
So that's a good question. So the question is, if you enable the RAID cache, do you disable the disk cache? And the answer is absolutely yes. In fact, and I have a slide a little later on this, but most host bus adapters will automatically send SAS or SATA commands to turn off the write cache on the disk, because again, the bottom line is it's never safe to enable that write cache on the disk, because effectively, if you write to that write cache with no battery on it and it acknowledges the write without getting it to permanent storage, you're opening yourself for loss of transactions and possible data corruption. Okay? Again, very few applications are sensitive to this, but databases are absolutely sensitive to this, right? So one of the ideas is to put a battery here. Another option, if you're using Flash, is to buy an SSD that has a battery. Instead of requiring a battery on the rate controller, we actually have a battery on what we call the staging cache. And in fact, the staging cache for an SSD is really quite a bit different than the cache on a disk drive. Because cache on a disk drive is basically just a copy of what eventually is going to be written. And if you turn off the cache on the disk drive, it's going to just have to write to the platters. Okay? But in an SSD, that staging cache is pretty much a requirement. You really can't turn it off. If you turn it off, then you're going to burn out your SSD very quickly. Because SSDs really only want to write in about 128K chunks of data. So if you turn off that cache, then you're basically going to be doing, your system's going to be unbelievably slow. Like 5% of typical throughput slow, right? So effectively, never buy an SSD without a battery in the staging cache. You can get away with it in a magnetic because, again, you can just write through it. You can't write through it efficiently on an SSD because of the way the chips effectively require you to write in 128K blocks. You can't randomly write at different locations in the same way you can write 512 bytes on a disk wherever you want to, okay? So again, incredibly fast. You get a lot of benefit out of this. I'm going to go into more detail. The last one I wanted to cover is DRAM. This is a case where you don't really have flash or NAND. You actually are using DRAM, okay? Unbelievably fast. Usually like a Fusion IO is the typical vendor for this. These always have a battery because DRAM, if you didn't have a battery, it would just go away, right? So by definition, it has a battery. Whether you need a battery on the RAID controller, I don't really think so. We've had a lot of debates on whether you need that or not. I would argue you probably don't. You just write it down. Because if your storage has durability, a lot of times your RAID controller just becomes a bottleneck. And you're just better off getting rid of it and shoving it down to the assuming you have a fast interconnect, just shoving it down to the storage. So you might think I'm kind of making up some of these stories. But actually, if you go to, and I'm pulling up a little terminal screen. Let me see if I can make it a little bigger. I thought I made it bigger, but it's still not big enough, is it? Let me make it. I think I have it at 18. Come on, where am I? Oops. No, I hit the wrong one. Oh, Control Plus? Okay. All right, that's a little bigger. So if I run the PG test fsync command on a magnetic disk, you're going to see some really pathetic numbers. PG test fsync is a tool that comes by default with Postgres. I think in Postgres 9.5, it's actually default. If you're on 9.4, again, you're probably on 9.4 because 9.5 is not out yet. It's in the contrib directory. So in the contrib directory, there's PG test fsync. And you can run this on your system. It doesn't do anything fancy. It just writes, does fsyncs, and times them. And what you're seeing here is writes to a Western Digital green Caviar drive. This is not a high-end drive. This is basically like an archive drive. I think it was like $150. I put all my movies and my family pictures on it and videos of the kids and whatever. So again, don't need high throughput. I think this is probably a 5,400 RPM drive or something like that. And you're seeing about the right numbers. Fsync, 80 ops a second, different fsync options. You get similar numbers. But again, you're seeing numbers in the 80s, okay, in terms of how quickly I can fsync. And then it's pathetic, but that's what it is. Fortunately, I don't run a database on here, but I would love to know the figure of how many people have their system throttled because they're having to do this kind of fsync. And you can see if I don't do the fsync, I get pretty good numbers, right? But again, you can run great if you don't care about your result, right? Now, if I go to an SSD and I run the same thing, and this is a battery-backed SSD, you're going to see some dramatically different numbers. So here, 9,500. So what is that, 100 times, 120 times what I had on the magnetic disk? 9,700, 10,600. So that actually turns out to be my best option for this particular server. So again, you start to see the throttle there, 80 commits a second or 80 fsyncs a second versus 10,000. That is night and day. And again, it's made possible because of the battery on the SSD. All right? Just to go over some terms, I've talked about write cache and write back. Basically, a write back means that it returns success right away. A write through cache is one where the data goes through the cache and to the layer beneath and then comes back. There are different caching layers. Again, this is merely text to kind of talk about what I already explained. You can have caching on the RAID controller, the HBA. You can have caching in the storage. And also, if you're using a storage device or a SAN or a NAS, then obviously there can be caching at those layers too. And again, they may be write through or write back, depending on how you configure them. You might be curious how you actually tell the operating system what to do with the cache. If you're on Linux, you can actually look at a file called HD Parm. I'm going to kind of pop down to the bottom here, but the HD Parm file in the etc directory on Linux effectively allows me to specify which drives have durable caches and which drives don't have durable caches. You can do this with HD Parm as well if you want to run HD Parm from the command line. But again, at boot time, this is probably the best place to put it. Effectively, what you have here is I've identified my SDA drive as having a durable cache. So therefore, when the system boots up, it knows it's a durable cache. It communicates to the drive and says, I know you have a durable cache. Make sure it stays on. What I have for SDB to SDE is I'm effectively turning the cache off. And I'm turning the cache off because I need those writes to be durable and because I know those devices don't have durable caches. That's why you got 80 transactions a second. If I turned on the caches on the magnetic drives, I'd get really good performance. But I wouldn't have durability. Okay, so again, it's a trade-off. What I love is the SSD because I get great performance and I get durability, right? Again, that's the etc HD Parm file. But again, there is an HD Parm command line tool, and also you can use HD Parm. You can look at the Postgres docs, and we actually have for Linux and FreeBSD and Windows, we explain exactly how to set your caching for each layer, and we talk about the different commands that you have. So again, something to kind of research when you go back is, I wonder how my sync system's set up, and I wonder if I'm losing any performance. Again, that was the real goal for this talk. Talking about some really details about actual hardware. Actually, any questions? Yes, sir. John. Do most SSDs come with battery backup? The answer is that in the first 2 years, most SSDs did not have battery backup. And this was disappointing. We felt that SSDs were going to change the world in terms of database performance. But it was not clear to us that the lack of a battery was actually causing the systems to corrupt if they lost power. Okay? Fortunately, with the advent, I would have to say, of the Intel 320, probably 4 years ago, there now were enterprise-class drives that actually did have battery-backed. And most enterprise SSDs do actually have a battery on them. Most consumer SSDs do not have a battery. So when you're purchasing SSDs for a database, you really almost have to required to make sure it has a battery. You cannot turn that cache off for reasons of performance, and sometimes it won't even allow you to turn the cache off. Yes, sir?
You might just point out that a lot of times on SSDs, they call a capacitor not a battery.
I'm sorry, capacitor. Yeah, supercapacitor, or a battery. It's not actually a battery. It's actually a supercapacitor, yeah. Right. And what they've done is they have the capacitor, and then they've got enough power to flush those to flush out the volatile data to the flash before they have to power down. Is really what the whole system does. So that's made it very easy. Again, years ago we would just love to have a little bit of durable storage. Now we have very affordable durable storage with a battery, with a capacitor, whatever. But if you don't have that, then all bets are off. So you really have to look at the spec sheet. Again, most applications don't care about durability, but databases do. So you really have to make sure it's there. Thank you. Yes, sir.
What kind of performance impact would it have if you left magnetic disk storage for
So what would be the impact if you used magnetic for storage of data and use an SSD for the write-ahead log? That's actually a very common configuration. SSDs are not significantly faster than magnetic for serial reads and serial writes, okay? Yeah, they're faster, but not, they don't blow the doors off magnetic. Where SSDs really win are durable writes, as I've explained, and random reads and writes. So probably the most economical situation would be to put your write-ahead log and your indexes on SSDs, maybe, and your data on magnetic. I'm not necessarily recommending that because it's kind of hard to manage, but you would get a definite benefit by just getting the write-ahead log on an SSD with a battery, with a capacitor. Totally. Yes, sir.
Considering what you just said, that sequential read writes are not that different in performance between SSD and magnetic, does it make sense to do the other way? Put data on SSDs and walls on magnetic. Because you just want to write it and then it's
So the question is, would it make sense, because I've said that it's the random I/O that's faster on the SSD, would it make sense to put the data and the indexes on SSDs and the write-ahead log on magnetic? There's two reasons that wouldn't work. The first reason, and the most important reason, is that there's two things about SSDs that are beneficial. One is random I/O, but the second is durable writes. We know that on a magnetic, durable writes are terrible. Again, you have to wait to get it on the magnetic platter. You have to wait for the thing to come around to the head. The head has to move to the right spot. Even if the head is exactly in the right track, you're still spinning around only 250 times a second. Okay? So you're only effectively, your maximum throughput for writes is going to be 250 writes a second. Okay? So although you would think, you're right, write-ahead log is sequential, why not put it on SSD? What you don't have is the ability to quickly, durably write to magnetic. Okay? The other advantage, I think, to putting the write-ahead log on SSDs is the write-ahead log isn't that big. I mean, maybe it's 500 megs, like a gig maybe. I mean, it's tiny compared to even modern SSDs. There's just not a lot of write-ahead log there. Each write-ahead log file is 16 megs. If you have 100 of them, what is that, 1.6 gigs? Like, it's not that much, right?
a very weird application where walls run into hundreds of gigs a day, whereas the database is only 500 gigs.
Okay, that's interesting. So you have a case where you're generating a huge amount of wall, and the walls are not getting recycled?
No, we want to keep them for recoverability.
Okay. So you want to keep them for recoverability. What we're basically going to tell people is when you're keeping your wall for recovery, don't keep those on the SSD. Archive those off to maybe another machine or another drive on the same machine, right? I would want to get them, I want to get them off of the drive that has the write-ahead log, so I have a separate place to store them. And also, we don't care about the time it takes to write those things, right? Because that happens asynchronously. So it's just the pgxlog directory alone that we care about, not the rest of it, right? So that's a good point. Get the archives out, the actual pgxlog directory, which you can symlink somewhere else, even within InnoDB, you could just symlink it, shut it down, move it, restart it, whatever. There's a flag at InnoDB, you can move it around. And again, that's really where, to me, that's where the gold is, to getting your write-ahead log on an SSD with a battery. That's where the gold is. The silver starts to come when you get your indexes on SSDs and you can start to do some random I/O really fast. So again, we're still kind of, we're a couple years in, but we're still kind of learning, I'd say, some of that stuff. Other questions? Yes, sir.
Is there a disadvantage to have, let's say you have a 6 terabyte array, and having your data, and so you have one drive, the data and the wall logs on the SSD?
So are you asking, so the question is it make sense to put the write-ahead log on a different drive, a device than so if you have a 6 terabyte system, odds are it's multiple drives that are in a big cabinet. Usually you just throw the data at it. You don't bother usually splitting it up. I haven't seen a huge amount of advantage to that. I'm going to talk about, is this a SAN? So I'm going to talk, it's attached, but it's a big array, yeah. I mean, some people put them on separate. If you think you're going to be writing a lot and you want a dedicated channel, I would actually not so much worry about the individual drive, but like have a separate channel that you can just flush the write-ahead log to that and not have it interfered with all sorts of other I/O that's happening in the same cabinet, there is some advantage to that. Yeah, I would think there would be some advantage there. Not going to be huge. Not going to be huge. Great. Other questions? Okay. So let's get into some details. Again, I've kind of been the 10,000-foot thing here. If you are using magnetic, again, there's nothing the matter with it. We just need to understand the performance characteristics. You probably want more spindles rather than fewer spindles, meaning a lot of smaller drives versus a lot of big ones. RAID 5.6 is just way too slow for databases. The writes to a RAID 5.6 is just, you're having to write to multiple drives. Like, it's just really bad. I know some people use it, and again, for low volume websites, low volume databases, it's fine. But if you're going to do high volume, you really want RAID 10. Pretty much everyone who cares about performance is doing. If you're looking SAS versus SATA, I'm not really wedded to one of those versus the other. But be aware of when you're buying an enterprise drive and when you're buying a consumer drive. Enterprise drives, again, are designed to have very good reporting. Smart tools, make sure your drive has smart reporting and turn it on. Anybody who hasn't run smart CTL on their server, shame on you. If you have bad hardware, you want to hear about it as soon as possible. And smart CTL is going to do that for you. So make sure you buy drives that report their smart settings, and make sure you run smart CTL as a daemon so it runs occasionally and it reports the problem. So for example, if I look at, let me just do it for my SSD, smart CTL-A, and I'm going to run it on my drive. You can see it's reporting a whole bunch of information. It even tells me my media wear out indicator on my SSD. You can see here it's 95%. It actually used to be 99% until somebody ran a week's worth of upsert tests on it. So you can actually make that indicator go down, I found, yes. But good for them, we got the feature, so it was worth all the pain. But again, make sure you have smart, usually what I tell people, and the problem is everything kind of looks the same. Like, how do you know it's an enterprise drive? How do you know it's really designed to be run 24 hours? How do you know they haven't cut costs? Because a lot of times, they'll be like, we have to get a drive at a certain price point, and if you're cutting corners to get that, if you're cutting reliability corners to get to that price point, is that really where you want to be buying? Is that really the product you want, right? But then when you look at the actual drive, you can't tell. It looks the same as every other drive. So how do you know what's inside, right? So it becomes very hard for purchasing to kind of figure out what's a drive. If you take a look at that URL there at the bottom, it kind of explains the concepts that go into an enterprise drive versus ones that go into a consumer drive. And usually you can look at the warranty as an indicator of kind of how much confidence the vendor has in the product. And that's like the only number I can really be sure of. Because if they think it's going to fail a lot, they're not going to give a long warranty. SSDs, again, there's flash SSDs, there's DRAM. That staging area is not just a cache. It's actually a staging area. You really don't want to ever turn it off. A couple settings here in terms of, I mentioned that it's best for random writes and wall, like indexes. Couple settings here. Random page cost. If you are using SSDs in your environment, you're probably going to want to change random page cost. Here I've set it to 1.1, which is usually the sort of community setting that we put it at. One of the interesting things is you can have a different random page cost per table space. So again, if you have a mixture, you can have one table space with a random page cost of 1.1 and one of them with a default of 4. Similar effective I/O concurrency, we found that, again, because you're not worrying about a spinning thing that has a very slow throughput, increasing effective I/O concurrency actually has a lot of advantages for an SSD. And we had a discussion actually 2 weeks ago in the community about why that is. Because you would think that the SSD would return the results so fast that there was no sense in doing effective I/O concurrency, but in fact there is. So we've seen some real improvements there for SSDs using that. And again, here at the bottom is an older blog post really talking about the Intel 320 SSD. but effectively going over the importance of that durable storage and the capacitor on there, and explaining why that is so key. File system options, we usually prefer XFS or ext4 over ext3. ext3 has some problems with sort of aggregating fsinks in a way that's not efficient. You can reduce file system logging or A-time if you want to. I haven't seen a whole lot of research that that's a win, but again, you might want to look at that. Battery back cache, again, you want to verify its existence, make sure that actually it's there. Usually it's a capacitor, but again, older models might have a battery. If it's a battery, then you're going to have to replace it, and you're going to need to know exactly where that is. Here's a picture of an older RAID controller. Just to give you a picture, you can see that blue area up there at the bottom left is in fact the battery. And in fact, if I blow it up, it indeed says lithium-ion battery, and you can see the little cable going over here and the little beeper when the battery is dead. So again, this is an older model, but you get the idea of having a capacitor, the idea of there actually is something there that makes that storage durable. Newer systems, again, have a capacitor. They would not be losing power. You wouldn't have to replace the battery in the same way. Shared storage, I know many of you are using shared storage. There's nothing the matter with using shared storage with Postgres. Just be aware that it is a shared resource. So because Postgres is very sensitive to I/O concurrency and returning results quickly, you want to make sure that you have that ability there. So I know it's easier to manage usually on a SAN, okay? Because that's where all your data is. You back it up together. You can allocate data really easily. That's great. Just be aware it's a shared resource. You're going to have some issues potentially for very high volume. Also keep in mind, if you do some really complicated things with having like 5 different storage layers and like having the data move transparently from one storage layer to another when it's heavily used, that can interfere with your database because, in fact, the caching layer of Postgres makes the SAN think that that data isn't being used very often, so it gets moved to slow storage, and all of a sudden you write to it, and then it's, oh, I got to go get that thing back. So a lot of cases we've seen people who have had SANs who have tried to enable some of the more sophisticated management features have basically given up on the management features and just allocated some fixed storage right to the database. Okay. RAM, obviously super important. It helps to reduce the pressure on your I/O system. The more RAM you have, obviously the less you have to sort of pull data back and forth. Again, reminding you, these slides are on my website, so anytime you want to look at them, you'll be good. The RAM reduces the I/O requirements. Again, if you can get enough RAM so you have 5 minutes of working set data, you're golden. Then you're going to be I/O bound. Then you're going to be CPU bound, and that's really what you want. Again, ECC RAM, don't go anywhere without it. The more RAM you have, the more it can fail, and the more cosmic rays can cause problems, so don't go there. And finally, CPUs, just wrapping up. Again, I left CPUs for the end. Postgres doesn't allow you to use multiple CPUs for a single query, but again, we use multiple CPUs for multiple sessions very easily. If you use a lot of server-side functions, you might generate a lot of CPU load. Or if you have so much RAM that everything's coming out of RAM, you're not having to hit the I/O, you're not having to wait for I/O, then in those cases you can end up being CPU bound, and that's good. That's a good thing. If your database server is pegged on CPU, consider that you've done your job. I know it sounds stupid, but what you don't want is have idle CPUs and have poor performance. And finally, one of the challenges I think is that a lot of these things look the same. Like these two cars have steering wheels and gas pedal and a door and so forth, but they're different cars. And how do you determine what a quality car is? A lot of times when you're purchasing hardware, you want to purchase it from a vendor who understands database workloads. They understand the trade-offs. They understand where to put the money, where to put the parts, where to get parts and put money into things that are going to last for a database. not for a gaming machine in a lot of cases. So again, just try and get vendors who can adjust to your demands. And when you say it's for a database server, they're like, oh, I know he's going to need this. I know he's going to want that. And you don't have to lead them down this entire presentation to do it. So thank you very much. I unfortunately do not have time for more questions, but we did get a chance to answer a lot of questions during the presentation. I hope you have a good conference, and thank you for attending.